Hi, my name is Patrick Mills. This is challenge 1 for EC461 with Dr. Graves. I'm just going to step through my code here of how I erase and write to flash main memory on the MSP432. I'll walk through what this does and then give a little demonstration, both in software and of the hardware itself. So top of my program, I just have my declarations and function declarations, and this flash sector array, which is what's going to hold all the different sector locations that I'll be writing to. So coming down to the main function, to start, I hold the timer while I'm initializing the board, and then it'll restart when the code starts. So it calls this port init function, which you can see down here. All it's doing is setting up switch S2 as an input and the green and red LEDs as an output, and turning those off to start with. And then I disable my interrupts because we're not using any. Set up my clock to 48 megahertz and prepare flash bank 1, which is the main memory that I'll be writing to. And then I set the watchdog timer to perform a soft reset upon a timeout condition. And I get to my while loop here, which this is just going to run continuously over and over. And it's where all the work is done in the program. So it just sets up and starts the watchdog timer with a value of 1 second expiration, data by this parameter. And then I run this function called erase and program flash, which is where it does all the work. And how this works is, see, I define some variables here at the top. Basically, it's just a for loop that runs 32 times, so 1 time for each of those memory sectors. Each memory sector is 4 kilobytes, so it'll add up to be the full 128 kilobytes of memory written by the end. And what it's doing, so I'm polling to see if the button is pressed in this, which is how I handle the watchdog timer force timeout condition. So if the button's pressed, it's going to force, and you hold the button for more than a second, it's going to force that watchdog timer to timeout, and it'll see that here and just turn the red LED on and flash that. Otherwise, if the button isn't pressed, it's basically just going through unprotecting the current memory sector. So the for loop is using an I variable. It's going through the sectors one at a time, so it'll unprotect that sector, erase it, and then write the new value to it, which I have it set writing this hex A5 value repeatedly. And so once it writes, it'll reset the watchdog timer during normal operation to prevent that from going off, and then it'll just loop over and over and get through all 32 sectors. And then once you get through all of that, it'll toggle the green LED for 1 second per the spec. So and then it just resets the starting memory location, so it can keep doing that loop over and over again because it's in this while one, and it'll just do that repeatedly. Alright, now I'm just going to walk through a quick example with some breakpoints showing kind of what this code is doing in the memory. So you can see I've got the memory browser pulled up on the right. I've got it at location hex 20,000, which is the first location in main memory that we'll be writing to. And so I'll just go ahead and start this. So I started the debugger, and we hit the first breakpoint, which is in the erase and program flash function, and I've just got a breakpoint set here before it really does anything, so you can see the starting memory values before the erase write. So it's hex Fs all the way through. The values that we're looking at is from 20,000 to 40,000. So you can see it ends here. And then, so I'll just step through this. So the next breakpoint it's going to stop at is before the erase. So it's going to yield the same values, and then we're going to do the erase. And so the erase actually sets these f's. So even though the values didn't change, it did erase these values. So that's what they started as. And so the next one is writing the values, and remember it should be writing the value of A5 that we set up here, and the min set up there. So I'll go ahead and step to the next breakpoint, and you can see here on the right that we wrote this A5 repeated, starting at hex 20,000, and it's 4 kilobytes, so it's going to go all the way up to 20FF8. You can see that there, and then 2100 still F's. And so, I mean, you can just keep stepping through this as much as you want, and see how it writes the next values there, and that would take it to 22,000. You can see that there. And so through the end of it, if I just take these breakpoints out, and then plus we'll have a breakpoint after we finish going through the loop 32 times. So you can see that all 128 kilobytes have been written. And I'll resume and let that go until it hits that point, which takes a few seconds. And there it is. And so that should get us all the way to hex 40,000, which would be 128 kilobytes. So type that in, and sure enough, it's written the A5 all the way to 3FF8. So it's gone from hex 20,000 all the way to that value there. 128 kilobytes of flash main memory locations have been written. We can see that is successful. So from there it would go on to toggle the green LED to tell you that it's done all that. And then I would just keep repeating that. And the next thing I'll show you is just a little video of the actual board doing this. Alright, this track here is really just demonstrating the board running. So I have the program running on the board right now. You can see the green LED just flashed. So it's going to flash every 9 or 10 seconds. It runs through that program faster than every 60 seconds. There it goes again. So this is normal operation. Now here's another example where I'm going to press the button and force the watchdog timer reset timeout condition. Alright, so the challenge 1 rubric wanted us to consider the optimization of the code, specifically the advice that CCS gives to optimizing the code. So I'm going to do that now. You can see after building the code, which I just did here, bottom right here we got some advice on optimizing our code. It says right here, not all available code size being used, and this is about finding the best speed versus size setting. So double click that, say that we're trying to get more speed optimized out of this, start the optimization analysis and let it do its thing. Alright, and there it goes. Got some results here. Well, that is it for the Challenge 1 demonstration video. I hope you enjoyed the video, and thank you for watching.